All right, recording is rolling. It's Monday, February 20th. So my honors classes, you guys are turning in this page here. This is chapter 13 puzzles. Now you guys know there were a couple of problems that we did not do in class. So number 80 and also number 95. Don't worry about those. We didn't do them in class. If you had a fun challenge doing them otherwise, that's cool. But I'm just going to grade the ones that we did do in class. My conceptual kids, don't worry about these because you guys haven't seen this, but I'm getting everybody the same civil engineering presentation today because that was my my undergrad major. So I'll show you guys what I know about that. How many of you know what a sieve is? What is a sieve? All right, well, you guys are going to see one of these in the civil engineering presentation today. I'll point it out. There's going to be a slide for that and what it's used for. And next couple of days, we're going to break out the cardstock and the glue and have you guys construct a sieve and actually use it. Right. Then, oh, you guys know the SAT is coming up next Wednesday, so a little over a week from now. Now, most of you guys are going to take it because I think it's given to all juniors. How it goes. So we're going to take Thursday, Friday. We're going to do SAT practice. Then I'll go over the answers to that on Monday, Tuesday. We're just going to do the math section because that's what I can actually help you guys with. And then get you guys at least a little bit more ready for the SAT. You guys remember cell phones being phased out by next week, so look forward to that. Okay, and I just gave you guys a take-home quiz. So, well, conceptual students and honor students have a little bit different looking quiz, but let's have this take-home quiz due Friday. So there you go. All right, so everybody good with what we're doing? All right, let's switch over and get this civil engineering presentation going. All right, is this really gonna do this? All right, let's see. I was trying to not do that. Well, okay. How about this, maybe? All right. Okay, so try to fix that for the recording. I don't know. We're gonna see. All right. So civil engineering. So again, this was my undergrad way back in the day. Here's most of the classes that I took to get degree in civil engineering. So there were a few general classes. There was one class that was just an engineering overview. So if you're good at math and science and engineering and that sort of thing interests you, maybe you want to know more specifically, hey, what would a civil engineer do compared to, say, mechanical engineer or industrial engineer or chemical engineer or aerospace, something like that. Right? Like main difference between here, just pick a couple of examples, like civil and mechanical, for example. Civil engineers usually build things that are static, right? So big buildings, bridges, roads, sewer systems, that sort of thing. Versus mechanical engineering, you might be more interested in if you're doing more like robotics or you want to design a factory with moving parts, that sort of thing. I did take a class on writing communication, so that was like essays, communication geared towards engineers. I took one programming class. So if you guys know anything about computer programming, then got a head start there. It's awesome. It's a class on ethics. Here's some of the math process. Well, okay, actually I didn't take a trig in college, although you can, they usually offer it. But you guys know how fundamental trigonometry has been just in this class of physics, right? And physics is definitely fundamental to engineering. So, I mean, how many times have you guys taken sine and cosine components, right? So that's trigonometry there. Calculus classes, you'll have to do those. Now, some of you guys are in calculus, so you're familiar with what this is, but if not, crash course here. Calc 1, just in a nutshell, has to do with rates of change. What's the instantaneous rates of change of something, right? And there's all kinds of problems you can solve and things you can do with that. Calc 2, just in a nutshell, again, like oversimplifying, is kind of the reverse of that. So you're aggregating incremental changes. It's called integration. Calc 3, man, remember that 830 class. That's like calculus in 3 dimensions. So you got some like, well, again, like in a nutshell, I'm just simplifying the bits I happen to remember from many years ago. So if you have some strange like 3-dimensional type object and you want to know like, hey, what is the slope with the z-axis with respect to the y-axis or something crazy like that. Statistics. I'll tell you what, like these top 3 classes I did enjoy a lot: trigonometry, calculus, statistics. Statistics, we're going to do a little bit in this class in the future. So I'm going to build that in with quantum mechanics because there's a tie-in there. But statistics you can use all over the place to like reject null hypothesis and all kinds of science investigations. Here, I'm going to use kind of a silly example with this, but just to plant an idea. Suppose there's a machine that's putting M&Ms in an M&M bag, right? And so you got this design, somebody just presses a button and is just loading bags with M&Ms, right? And there's supposed to be like 20 M&Ms per bag. Like that's kind of what's advertised. Okay, so 20 M&Ms, right? But the machine's not perfect. You're going to get plus or minus factor. Some bags have 18 M&Ms, some have like 25, right? And maybe you go and you buy a bag of M&Ms. It only has 10. 10, I feel ripped off. So maybe there's a consumer protection agency that says, well, how close is the advertising compared to what they deliver, and like what's the plus or minus factor, right? I mean, that is like one of like many. That's probably not even like the best example, but that's something that you could solve with something like statistics. Differential equations. Oh boy, this is a class that really kicked my butt, but high-level math you can do all kinds of cool stuff with. I mean, I've seen the term like Fourier transform used in all kinds of crazy technology applications. One problem I do remember being solved with in this class actually was a physics problem. It had to do with terminal velocity. So you drop a ball, it faces air drag and eventually reaches terminal velocity. Now, in this class, the way we approach it is, well, first we ignored it for many weeks. We said, assume there's no air drag at all. And then when we did assume there was air drag and terminal velocity, we said, okay, well, it asymptotically approaches that. So we'll set up 3 diagrams and say, what could it approach? Set drag force equation. Now, in this class, you can actually solve more specifically, like if it's been falling for 17 seconds, like how close is it to that value of reaching, right? Which we didn't quite touch in this class, but I could see how that could be important for something like aerospace, right? If you're designing planes, right, your rockets, right? Science classes, a couple of physics and a couple of chemistry classes. Now, physics 1 in college mostly focuses on the stuff that we did last semester. So a lot of mechanical type stuff, kinematic motion, dynamics, energy, momentum, that type of stuff, rotational. Physics 2 tends to focus on electricity and magnetism. Now, in this class, we're going to hit DC circuits, so we're going to just barely touch on this, right? Then if you take Physics 2 with Mr. Gentile, you'll go more in depth with electricity and magnetism. Now, high school physics 2, it's usually also where they put more some stuff that we're actually kind of doing right now, like Bernoulli principle and fluid dynamics and waves and that sort of thing. All right, so a couple chemistry classes, right? Okay, and then all these engineering specific classes. Now, almost every one of these, I do have a slide for, so I'll just go over these as I go through this presentation, right? And then, okay, great. So zoom out here, next slide. All right, statics. So this was one of the classes I took, so a whole semester class. Suppose you're designing a structure. Now, so civil engineering, static structure, hence the word static, it's not moving. You know that every single point in your structure has to be in equilibrium, right? Because it's going to be at rest. That's the type of equilibrium, which brings you to these equations right here. Now, if you're looking at just a 2D cross section, you can simplify it down to these 3. So the sum of the forces on the x-axis and the y-axis each have to go to 0 newtons. And also the sum of the torque has to go to 0 Newton meters. Now that could be on the xy plane, or if you like, you're about the z-axis if you bring in the right-hand rule, which I touched on briefly last semester. There's a poster back there. You guys see right-hand rule, you like point different directions, right? R cross F, like opening a door. You guys remember that? Now, if you're thinking in 3 dimensions, that actually opens up 6 equations. So the sum of the forces along each axis, x, y, and z axis have to go to 0. And the sum of the torques around each plane, or you can think around the perpendicular axis to each plane, also has to 0 out to 0 Newton meters, right? Or foot pounds, I guess. I forgot about foot pounds. Oops. Right. Now, again, those equations will carry you a long way through this class called statics. So here's a cross section of a truss system down here, right? And you can see. I mean, you would want to know if you're an engineer designing this thing, well, which components are under tension and which components are under compression. You guys see the whole top of this is under compression, right? Oh, look at this, 96 pounds, 77 pounds. In this class, we use newtons, not pounds, but same idea, right? And look at the bottom. These are all in tension, right? So we got 48 pounds, 86 pounds, like, was that 38 pounds? So, I mean, first of all, you want to know compression or tension, because here's for one example. There's certain materials that you can build with, right? And they have different compressive or tensile strengths. Concrete, for example, has almost no tensile strength. It's really good at compression, but it's like terrible at tension. You pull on concrete and it'll just pop apart. So you would not want to have any structure that had concrete that was under tension because that wouldn't make any sense, right? And then, okay, so let's say you're building this out of steel. Great, you're building it out of steel. Well, you still have to know exactly how much tension, because that's going to correspond to, like, if you know what this force has to be, you'd want to scale it up to have some cross-sectional area. Like you probably want to use a big, thick steel rod right here, right, compared to this one, because there's more force going on here, more tension force, right? But again, this is like an optimization question. There's also an economic side to this whole thing. I mean, somebody's buying this bridge. Maybe it's a private company, maybe it's the government, but somebody's looking for like a low cost. So you want to design this as an engineer to like minimize costs, right? So you want only the piece that you need. And the way you solve this with these equations is you can go around to every single one of these truss joints, and you can apply all these equations. So the sum of the force goes to zero, the sum of the torque goes to zero, and that's how you can calculate every single one of these tension and compressive forces. Catenary arch. So let's start with the catenary chain. Zoom in on this guy, top left. If you hold a string or a chain at both ends, it will form this shape, which at a glance might look kind of like a parabola. Actually, it's kind of close. People 500 years ago suspected it might be a parabola. It isn't exactly, and we've known for at least 300 years, there's been a proof going around that it's not exactly, it's a little bit different equation. But if you think about every single link in this chain, sort of has like minimized tension because it just naturally sets up to that shape. So think about that. If you were to make that rigid and turn it upside down, you can get a catenary arch, which is also an optimal shape, right? Good. It will like maximize the strength of your design to have like this catenary shape.
What is it if it's not a parabola?
I think it's like a hyperbolic sine function, I think is what it is. It's something I don't actually know. don't know the equation for. You have to look that up, but yeah, something like that. St. Louis arch is a modified catenary because it's actually a little bit thinner near the top than on the sides. Right? So again, like if you had the shape and you dunked it upside down, it would want to be that shape naturally, right? So you turn it upside down, make it an arch, right? It's like as strong as it could possibly be. Right? I-beams. So you see these used all over the place in construction. Well, what's the deal with this? So I'll give you guys a simplified example. Suppose this is on two supports, one on the left end here and one on the far right end. It's a couple supports, right? And I've got a huge weight pushing down on the top from the middle. Does this want to bend kind of like a smiley face? Want to bend, you guys think? And if it does want to bend like that, I'm going to flip back a couple of slides. That kind of reminds me of this, where all the top is in compression and all the bottom is in tension. That would be true, wouldn't it? Right? But by the way, one project I want to have you guys do before spring break is to build a toothpick bridge. So give a good look at this, because this might give you some ideas about how you can optimally design a toothpick bridge, right? Where, you know, if you've got support on both ends, and you got a huge weight in the middle, which is how we're going to run this. That whole top end is going to go into compression, and then the whole bottom is going to go into tension. So start thinking about this. Some other clues too you might pick up on, right? So if all the top is in compression, all the bottom is in tension. Yeah, that's just the specific example I'm picking, but just a simple example. All along the middle, it's going to transition. And in fact, there's some axis in the middle where there's no stress at all, right? Where it's like transitioning from tension to compression, right? And since most of the tension compression happens in these top and bottom flanges, that's what these are called, by the way, flanges. Well, that's where you want most of the material, right? That'll carry most of the stresses. And if this is embedded in, say, like concrete or surrounded by concrete or some other material, it also provides an economic solution, right? Which again, it's like the other half of this. You have to think, well, somebody's paying for this project, because steel is much more expensive than concrete. So, you know, if you can just have the steel exactly where you need it, then it'll help minimize cost too. Right. Something else I-beams is you can calculate a moment of inertia with these, and they have a pretty big moment of inertia per unit of material that they actually use, which also gives it a lot of strength. Hey, have you guys ever thought about cardboard, right? If you can take cardboard apart, and it's just like really flimsy paper that tears really easy, right? It's just like the weakest paper in the world. But if you have this corrugated shape, now you can make a cardboard box where you can throw all kinds of heavy stuff in it, and it will like carry a bunch of heavy stuff without falling apart, right? Because this corrugated shape, that's like a bunch of little arches in there. It has a huge moment of inertia. It gives it a bunch of strength. Another example where you see something pretty similar to that, if you look at the design of a washing machine, the whole outside is just this really flimsy sheets of metal, but they have these rigid indents, which again gives it like a corrugation effect, gives it a moment of inertia, gives it a bunch more strength than it should have otherwise. Okay, so moment of inertia. Dynamics. Here's another class I took that probably applies more to mechanical engineering than civil. which because dynamics, like things are on the move, things are in motion, right? In fact, I remember when I took this class, being a civil engineer, they actually let us out a few weeks early. I only got 2 credits for this class instead of 3. Like almost all college credits are 3 credits, right? So 3 credit classes. Some are 4. Physics is a 4 credit class because you have a lab. So 3 for the main class, 1 credit for the lab. But this class I only took 2 credits worth. I actually enjoyed this class a lot, but it's really challenging class. Actually, my classmates and I call this physics on steroids, and you can see why. Like something like this cart in motion has a string tied to this weird Atwood looking shape. Right? Hey, what could be like the acceleration of this block going upward? That might be an equation as a function of time. Like that could be a really complicated scenario. Like as this cart's moving, maybe it's speeding up, maybe not, maybe it's slowing down. Maybe this tension is going to be changing. This angle beta is going to be changing, right? You got a lot of parts on the move. So if you look at each component part, it's actually something that you know from this class, right? Because we've done every single component part, right? We've talked about velocities and accelerations. We've done trigonometry with sine and cosine and beta. We've done tension and strings. We've done Atwoods. We've done all the component parts. Put it all together, it gets pretty complex. Remember my instructor for this too was working on self-driving cars. That was some of the research he was doing, which was really cool. Still waiting for those. They always seem to be like the last few years. It seems like self-driving cars are like 99% of the way there, and they're just like working out the last few things. But I'll put out one of those pretty soon. All right, concrete. Yeah, like there's whole like classes you can take for each one of these. So concrete. Now, concrete is a really cool material because you can pour it like in a liquid form, so it can take whatever shape you want, and then it will harden. Now, there's a misconception about it hardening. Some people think, here, look at the ingredients of this. So you got aggregate, so basically large rocks. There's also fine aggregate. So we got coarse aggregate, large rocks. We got fine aggregate, think like pebbles, sand. This could also be silt and clay. That's kind of a simplification here. I'll show you guys next slide. You actually want different size aggregate, right? But we're going to throw in now cement. Now modern day we use Portland cement, right, to make concrete. More on that here in a minute here, and also water, right? So you mix all these things together, and what some people think, if you don't know anything about concrete, is like you might think, oh, well, maybe the water evaporates and you're left behind with the hardened concrete. That's not how it works. What actually happens is that this concrete undergoes a chemical reaction with the cement, like in our case, modern day cement, like a Portland cement, right? And that chemical reaction is exothermic, so it releases a bunch of heat energy. Right, so the concrete actually cures, right? Kind of like Elmer's glue, right? Actually, there's a chemical process, right? Chemical reaction, right? And it will harden. Also, this process releases a bunch of carbon dioxide. One of the kind of big contributing factors to global warming actually is just concrete construction. Okay? Just this process here. Now, what about this? So this picture right here actually is not modern day concrete. This is ancient Roman concrete, because this is actually the underside of the Pantheon, which is over in Rome, which I think still to this day is like the largest like freestanding concrete dome that there is. So the Romans used a different type of cement for concrete. They used some kind of natural volcanic ash that they got hold of. And they could build all kinds of cool things with it. They could build, of course, concrete dome, obviously, you look in the picture of it. They could build walls, they could build aqueducts, they could build roads. There was one thing that the Romans could not build with concrete that totally stumped them. And that is what you guys are sitting on right now, which is the second floor, because we're on the second floor of a building, right? So Romans tried it, and those second floors would always just immediately crack and fall apart. That problem was cracked many years later, but coming up a future slide. So I wonder if we can solve that. Now, when the Roman Empire collapsed, a lot of technology knowledge was just lost in history for 1,000 years, including concrete. There was a good 1,000-year gap where nobody knew how to create concrete. And people were walking around Europe looking at aqueducts and something. How did they make this? Right? Had no idea. But concrete was sort of reinvented with Portland cement concrete, just within the last couple hundred years. Okay. All right, so let's talk about aggregate and sieve. You guys know you're going to build one of these next couple of days, right? So see, how can you create like the strongest type concrete? Because if you look at the ingredients here, the strongest ingredient going on actually is this coarse aggregate. Right? Those rocks are extremely strong and carry a bunch of stress, right? So you might start out, hold on, what just happened here? Hold on, whatever I did. All right, okay, back to here. So you might think, hey, maybe I want a bunch of like hard rock, a bunch of this coarse aggregate and cement and water. Maybe that will solve it for me. But here, let me zoom out on this one. What that ends up doing is the gaps between that coarse aggregate is all filled by cement, which is the weakest part of the concrete structure. So, hey, what if we took like some medium-sized aggregate and like patch those holes, right? We just mix in some medium-sized aggregate. But then you guys see where this is going. It's going to be a recursive process where, oh, well, now there's gaps between the medium-sized. Hey, what about like some sand or some fine aggregate, right? So if you want to get like the strongest concrete you can, what you really want is well-graded aggregate, well-graded. So you want all different sizes. So let's bring in the sieve. Here's a sieve. So a sieve is going to have all these layers to it, right? And every layer will have some wire mesh that has different size holes. So you put the largest holes near the top, and then medium in the middle, and then the small near the bottom. Then you pour in your soil sample, which is like your mix of all your different aggregate. Right? Pour in your soil sample, and all the large stuff stays on the top, right? And then the medium stuff in the middle, and then all the fine stuff makes it to the bottom. And only the tiny little like clay and dust particles actually make it all the way to the bottom. So it separates it out, right? You have to like shake it, like do so many shakes, right? And if you get a pretty even distribution, then you know you're going to have some strong concrete. Let's look at the graph of that. So you got percent passing by mass, and then the log of the grain size. So if you get some well graded, oh, look at this. It ramps up slowly and it tapers off slowly until it accumulates 100% of your soil sample, right? Versus something like uniformly graded, it's like you get nothing, and then bam, all at once, and then nothing. So that's not good because this uniform grade goes by another name. It's called poorly graded. So uniform grade is poorly graded. It's the same thing. Right? You might also get something like this. So what if you get a bunch of large aggregate and then nothing, and then a bunch of like clay particles, right? So that could be called gap graded, where you get here, like here's all the clay and then nothing, and then bam, bunch of large aggregate, so coarse aggregate. Right? So ideally, to maximize the strength of concrete, yeah, you want an even distribution of aggregate. Okay, so we're gonna build one of these out of cardstock and glue. I've done this project in the past, and it actually works. So I have a soil sample for you guys, and you guys will be able to shake it and shake it out, make this thing work. Right. Yeah, I remember one cool thing I did was actually make and mold concrete. So still got one of these samples. I should bring this in for a show and tell one day. So what is the strength of concrete? Now, one thing to know about strength of concrete is that it specifically has a compressive strength, but it doesn't really have any tensile strength. So you can never design a structure where you have concrete acting as some kind of has some kind of tension force, because it'll just pop apart and it's no good. But compressive wise, it can carry, well, it depends how you mix it. So I got this table of values. So now this is all the concrete you can have, but this is a pretty general table. Here, let's just use this row, for example, like 4,500 pounds per square inch. If you go to an American university, they're still working in American units, so you get like pounds per square inch. But here, I converted it for you guys. That's about 31 megapascals. That's 31 million pascals. That's what the rest of the world is using. Or if you like, how about this? How about 300 atmospheres? So you guys know we're sitting in 1 atmosphere of pressure right now, right? If you took the atmospheric pressure we're in and you ramped it up by a factor of 300, then this is what would happen to that concrete. Pow! It would bust like that. Right? It would literally like smash the walls around us, because even if it was equal pressure both sides, like that wall would bam, it would go just like that. So anyway, back in the day, we mixed some concrete. Right? Here's different ratios of these ingredients that result in these different strengths and what you might use it for. Right? We poured a mold, and then we let it sit for a whole week. So it's curing, it's going through this exothermic reaction. Right? And then pull it out, throw it in this machine, and then press until bam, it smashes. And that's how you know the compressive strength. Okay? Now, pounds per square inch, or pascals would be like Newton per meter. Again, you're usually working like megapascals for concrete. That's some kind of force per unit area. And at least the American cylinders are 4 inches diameter and 8 inches tall. So, okay, so 4 inches diameter. If I do pi over 4 times that diameter squared, that tells me the cross-sectional area. And then if I do the force from this machine, I can divide those two to get the stress. Okay. Speaking of stress, we've got a stress strain curve here. So what is stress and what is strain? So stress is pressure, but it's pressure applied to solids. So it's force per unit area. Here's my graphic down here. Now my graphic, I'm showing something with a tensile stress, like you're pulling on it. You would not want to do that with concrete. That wouldn't make any sense. But steel, maybe. Steel, you could do this. You could apply a tensile strength to steel, like pull on it. Now for concrete, just reverse the direction of the forces to make it compression, right? You're going to push on concrete, okay? Push, push, push. Okay. Okay. And when you apply a stress, force divided by cross-sectional area, that's what stress is. Could be in pascals, megapascals, PSI. A strain is going to result. Now, strain is just a percent elongation. So how much does it change its shape? What percentage does it change its shape? Okay. That's a change in length divided by original length. This divided by this, right? Will be a strain. And that stress-strain relationship is linear as long as you are within the elastic zone. You guys see, I got stress on the vertical axis and strain on the horizontal axis. By the way, if you're taking engineering classes in the future, you're going to see this graph all over the place. So you guys see this first part of the graph is a direct relationship. It's linear. And as long as you are within that elastic zone, then if you take the stress off, it just reverts back to its original shape. Okay. So that's kind of like taking a paper clip and clipping together two papers. And you take the paper clip off and the paper clip just goes back to its original shape, right? But what if you take a paper clip and clip together like 100 papers and then take the clip off? Now isn't it all like permanently warped, deformed? Okay, well, that's what happens beyond this yield strength, beyond this yield point. So beyond the elastic zone, that's like permanent deformation. Which, by the way, we're done with concrete by this point. Concrete just bam, end it right there. Concrete just goes push, 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 and then bam, just ruptures right here. So the rest of this curve could apply to metals like steel. Like steel might have this whole top section where there's some ultimate strength that's even greater than the yield strength possibly. But then you keep stretching it. You can stretch, stretch, stretch. It actually gets weaker. That's why this tapers down until bam, it ruptures right there. Okay, you guys yeah. You guys good with the stress and strain? Stress and strain. Okay, so again, big concept, civil engineering. Okay. Oh, one more detail I need to mention about stress and strain. Let's go back to this elastic zone. This ratio, stress to strain, the slope of this line has a term. It's called Young's modulus. That's what this says right here. So we'll zoom in on that. Young's modulus, the slope of this line, which is a material property. So concrete might have a Young's modulus. Steel has a Young's modulus. I mean, it might vary a little bit. There's different kinds of concrete and steel, but if you know what you're working with, it's gonna be some stuff. Okay, so here's an example. So thicknesses of steel. I've got a bunch of rebars here. So a bunch of different ones, bunch of different standards. Young's modulus. Oh, look at that. 240 gigapascals, 220 gigapascals. Okay, that's like almost the same number, right? Proportionally, right? You guys see it? So yeah, maybe it changes a little bit based on the shape of the object. Young's modulus. Okay, stress to strain. You know what else could expand something is a temperature change. I think we talked about this a little bit last week. So thermal expansion. So how much does something want to expand because of a temperature rise? Well, how much does the temperature rise? Delta T, like be in degrees Celsius, Kelvin, degrees Fahrenheit, as long as you know what you're working with. What was the original length? And what is the coefficient of thermal expansion? Now that's alpha in this context, is coefficient of thermal expansion. Right? There are a couple of weird objects that might contract with an increase in temperature, like I think water some temperatures. That would give it a negative coefficient of thermal expansion. But most objects have a positive coefficient of thermal expansion. You heat them up, they expand. Now, how much does it expand? Well, it depends. Are we talking about aluminum, brass, glass? Ooh, it rhymes. Steel, concrete. So here's a small table anyway. And they all expand differently. Or at least they want to expand. I mean, this might be, if it's just hanging out by itself, it would expand by that much. Right? But if it's part of a larger structure, maybe it's pushing against other components of that structure and applying new forces somewhere. Be thinking about that too. If you're designing some structure, it's made out of different materials. So we got concrete over here and brass over here and steel over here. Those materials are going to expand differently from like winter to summer. When they do, you're going to get different forces in your structure. Right? But you know what? Look at these last two rows, steel and concrete. You guys see 11 times 10 to the negative 6 and 10 to the negative 6? That's almost the same number, isn't it? In fact, it's not even true that they're exactly a set value for each of these because there's different kinds of steel. There's different kinds of concrete. There's actually a window of values for this alpha values, coefficient of thermal expansion. And those windows actually overlap, which is a complete quirk of the universe, but it's really, really, really good news that they do have the same coefficient of thermal expansion. Because what that means is you can create a composite material with steel and concrete. You can create steel reinforced concrete. Remember a few slides ago, I told you guys that Romans could not create the floor that you're sitting on right now. This is the answer to that. This is the solution. Because, okay, so let's say you try to create a floor. So we're back in 2,000 years ago with the Romans trying to build a floor. And this floor wants to bend like the smiley face. You guys see that? Which is okay for the top section. Like suppose it's like a meter thick. It's okay for the top section. That goes into compression. Concrete's okay with that. But look at the bottom part. The bottom part's going to go into tension, isn't it? Which concrete has no tensile strength. So, I mean, right, basically none. So that's just going to crack and fall apart immediately. And that's the problem the Romans kept running into. But you throw in some steel rebar, that steel has a tensile strength that could be like 10 times the compressive strength of concrete. So yeah, you only need a little bit of steel rebar. And you guys can see it here, right? That steel rebar is embedded in that concrete. So now you have a composite material. And the fact that, go back to the last slide, the fact that steel and concrete have the same coefficient of thermal expansion means that your structure, as you know, from day to night or summer to winter, you know, as things like cool down or heat up, these two materials will expand and contract together, which means it's not going to all crack apart. Again, it's a complete luck of the universe that happens to be the case, but it is. So yeah, lucky us. We get to be on the second floor because of this right here, because of this weird thermal expansion property. Yeah, so lucky us. Something else cool with concrete. There's a certain species of bacteria. Okay, forget what species, and I haven't fact checked myself, but there's a species of bacteria that actually excretes, I think it's calcium carbonate as a waste product, which can actually act as cement. Now, all your structures are eventually going to crack and fall apart. It might not look like it. Like if you look at the school, you might say, "Oh, this school can like last forever," or those causeways over the water, like they're going to last forever. Except that they don't, right? If you had a time machine and you watched a time lapse and just ran the clock ahead like a million years, like a million years from now, there might be like barely trace evidence that the school ever existed, right? At some point, nature's just going to take everything over, right? You know, unless it like fossilizes or something, right? But otherwise, it'd be hard to tell this was ever here. So things are going to crack and fall apart. So your cracks start to form. You have to go make repairs. But if you embed this particular bacteria and it goes dormant, right? And you also embed some yeast that can eat as a food source. Then when a crack forms, it gets exposed to the oxygen. It wakes up from its dormant state, eats the yeast, excretes the calcium carbonate, and boom, self-seals. So it's all good again. Right. Soil mechanics. Again, there's whole classes you can take on soil and soil mechanics. So this picture on the left, we're looking at the base of the Leaning Tower of Pisa. Why is the Leaning Tower of Pisa lean? Well, because the soil underneath it is uneven. Look at all these layers. We got different layers of clay, we got sand, and it's uneven. Now, they didn't know back in the Renaissance when they were building the tower, they didn't know anything about the soil underneath. They just built stuff and crossed their fingers that stuff wouldn't fall over. But nowadays, we know to check for these types of things. These pictures on the right are examples of construction projects where the soil was not tested before they just went ahead with the project. I don't know if these are like from undeveloped countries or something, or what's going on here. But yeah, it's one of these things that's easy to take for granted, right? You see a building, like, okay, it's sitting on the ground, I guess. But that ground also has its own mechanics going on. It's got different layers. Maybe it rains and those layers expand at different rates. Right? Maybe they settle at different rates, right? And you want to know that ahead of time. Right? So what you're building on, right? So that's interacting with the environment too. So how do you do that? Well, you're going to, so before the construction project begins, right, you go to the land and you drill down and you get these core samples. These are what these core samples look like. And that's how they know, like so many meters down, we got this type of clay, and so many meters down, we got the sand, and so many meters down, we got this bedrock, right? Or like, I guess you could also bounce sound waves off too. That's another way you could do it, right? Or you could just drill these holes, right? One trivia fact I remember from the soil class was, if you ever see like a pole with a sign on top, like this racetrack sign, or like, so it's like McDonald's or something. Do you guys think that you have to dig down about 2 feet and just plant this about 2 feet down to the ground? No way. That's just going to fall over right away, right? Now this looks pretty sturdy, right? Again, if we're in a time machine, we're doing a time lapse. You wait a million years. Eventually, somewhere within a million years, this thing's going to fall over, but not within our lifetimes, right? So how far down do you have to go?
Probably 3 times more.
Ooh, I like the factor 3. Yeah, right. Yeah, a third. Yeah, a third of the height of the pole. Wait, how'd you know that? Oh, you've actually worked with us. All right. Yeah. So yeah, a good rule of thumb.
Longer.
Yeah. Well, yeah. Again, we're looking for like maybe like a minimum case for like cost reasons, right? It costs to drill. It costs to elongate the pole. Yada yada. Yeah. A good rule of thumb is a third of the height of the pole. So if this pole is like 100 feet tall, say, okay, well, 33 feet, I have to dig down at least that far. Okay. Now, there's actually an equation that goes along with this. It depends on, well, what's the size of hole we're using, what kind of soil do you have underneath? There's a lot of other factors too. What's the weight of the sign on top? But yeah, good rule of thumb is about a third of the height of the pole above ground. That's what you want to go underneath. AutoCAD. So they might not call the class AutoCAD, but because I don't know, maybe that's like a registered trademark name or something. Maybe it's a brand name, but that's what you're going to be working with. So here's a software where you can design things. Right. So engineer, architect, when navigate this. I should make the point too. This is one of those classes where it started to really click for me that see, like when I started when I started college, I was going in as a freshman. I had this naive idea that, okay, college is going to last like 4 or 5 years. I mean, most majors are 4 years. Engineering is like a 5-year program. So, hey, after 5 years, I'm going to be like this fully equipped engineer, and I'm going to be able to design all kinds of cool stuff, and right, and I'll be like ready to go and like my package ready. And then by the time I graduated college, and this was like one of the sort of later class I took, I forget if it's like 3rd or 4th year, I was realizing that it's not exactly true. So, just to be aware of this, so aren't as naive as I was going into college. What college really is you take a bunch of classes where you're exposed to a bunch of different ideas, and you learn a lot of stuff, but you really learn like fundamentals of how things work. And same thing with AutoCAD. I didn't do like this exact detailed design. I learned like the fundamentals, like here's how you like design lines and walls and stuff like that. But then like anything you apply this to is really kind of up to you. So you can take this program home. There's a lot of times there's like student discounted versions if you're a college student, right? And you work with it yourself, and you poke around with it because it's fun to do and you have an interest in it. And then whatever company you're hired with, basically the first year or two, they expect you to not really know much, right? So you're coming out of college, you know all the fundamentals basically, but then you have to start applying it. You have to apply it to whatever job you're hired to do, whether it's a private company or the government. Right. Water treatment. So one thing that's really nice about living in the States, I mean, there's a lot of nice things about living in the States, but one thing is you can turn on the tap and know that you're going to get clean water, right? So this is all EPA regulated. That's not true everywhere in the world, right? A lot of countries that you travel to, especially if it's not exactly a developed country, be careful. Like the locals might know that if you turn on the tap, you have to boil the water first before you drink it. You have to boil it before you cook with it. Like in the States, it's clean, right? So the water comes from like Somme Water Reservoir, like here in Brevard. I think we get it from St. John's River. I think that's where we get our water from. Right. And then go through a separation process, right? Get rid of all the all the dirt and stuff in it. Right. There's a ton I forgot from. I mean, this is like a whole semester class, and I've forgotten so much from this class, right? But I remember a couple of tidbits anyway. I mean, all these slides, right? So one thing I remember is this disinfection stage, right? So we've cleared it out. It looks clean from a glance, but you might still have a bunch of bacteria in it. Do you guys know what in the States we use to disinfect the water?
Chlorine.
Chlorine, yeah, chlorine. We use in the States. Do you know what's more popular in like the Netherlands or Europe? It's not chlorine. What do they use? Ozone, right? So in the States it's chlorine. Over there it's ozone. I want to say Japan uses ozone. I did a quick Google check. It looked like it maybe. So anyway, in the States we use chlorine, and each one could have a certain advantage to it.
What are the advantages?
And so one advantage of ozone is that, well, I mean, chlorine's safe in the low levels that we use it, but it does have like some environmental impact, right? But ozone eventually, I think, just decays into oxygen. I think give it enough time. So, and also, what is ozone? I think ozone actually purifies it faster. I think one of the advantages of chlorine is that it lasts longer. Like if you have like bottled water, if it's been cleaned with ozone, then that ozone will eventually dissipate into oxygen, and if there's some bacteria in it, it could like overtake and make the water not clean sooner. But if it's chlorine, that chlorine will just stay in the bottle and just keep the water clean like a longer time period. So yeah, so each one has a certain advantage to it. At least that's what I remember. Right. Something else I remember from this too is that like, can you just have a single textbook that says like, oh, here's how you build a water treatment plant, and then just like copy paste that everywhere in the world? Well, no, because every locality has a unique water reservoir with different environmental unique situations, different pollutants, different things you have to clean out. So if you are an engineer one day designing a water treatment process, you have to know what locality you're designing it for and then design it around that. And these stages might be different too. So like you might not have the stage or you might not have the stage or right. So it depends on what you need for that particular locality. Okay. Wastewater treatment. Okay, so great. Now we've used the water. Now we're like flushing toilets and letting the water go down drains. So now what happens to it? Well, you don't want to just dump this out into the environment, although that's the easy thing to do, but that's not the responsible thing to do, right? Because you can cause environmental problems. So you have to treat it first. Yeah, so kind of a trivia idea. One weird thing I remember my instructor mentioning was that water treatment is usually like square shape and wastewater is usually like this round shape. Forget exactly why that is. There was speculation last class that might have to do with like a centrifuge type. If you have like something rotating, which I guess that can make sense why, right? But if you're like looking at aerial photos from above, hey, there's some kind of water treatment plant. Is that regular water or is that wastewater? If it's like round shape, it's usually wastewater. Okay, so we got this wastewater. You can like try to separate it out. There's like stages where I forget what the term was. There's like some like bacteria that like eat this up and can clean it out that way. You might sanitize this. Sometimes, depending on your design, you could just like burn it, right? Sometimes you can burn it and like burn the methane and actually extract energy out of it. It could be like a partial energy plant too, right? But anyway, again, this could be like unique per locality or per situation. These could all be different things. So you got to clean it before you send it out back into the environment. Roads, right? So yeah, like designing roads, right? So road design is like modern road design is based on this Scottish design called McAdam design, where way down here in the subgrade you use like large aggregate and they get successively smaller and smaller aggregate size until you get to the surface. So that surface road that you look at and you see you're driving directly on, that's only the top layer of this whole system underneath. Now that you want this to be sloped a little bit, right? So that when it rains, like you don't want the rainwater to like puddle in the middle of the road. That would not be safe at all. You want it to run off on the side. So you need a slight gradient for that to happen. Right?
Somehow it still puddles.
Yeah, yes, sometimes, right? Like over time, right? I mean, over time things crack and fall apart. And we're talking about like 2-ton vehicles like driving over it. It's gonna warp it, potholes are gonna form, the road's gonna warp. Yeah, so you do need to like repair this every so often. And speaking of which, like what's the more cost-effective way to repair something? Should you like make small repairs as time goes on, like, ooh, there's a pothole, immediately patch it? Or would it make more sense to say, hey, look, because I mean, usually government is responsible for taking care of roads and that's paid for with taxes, right? So would it be a better idea to say, well, there's only some small cracks and small this and small that. So we'll let things go for 5 or 10 years and then we'll raise the tax money to repair it then. Like, what do you think is more cost effective in the long run? Like given like 50 years have gone by, what's more cost effective? Yeah, the first option, make small repairs as go along, which, a lot of people's gut reactions like, oh, but taxes are up today. Yeah, but in the long run, it actually saves money to do it that way. Okay. And then what material is actually used for the top layer? It's actually asphalt concrete, which is a different type than Portland cement concrete, although you can use Portland cement concrete too. Each one has its own advantage. So asphalt is quieter, it's more like rubbery, it's easier on tires. Portland cement concrete, on the other hand, lasts longer, it's more durable, needs less maintenance. Right? So last thing here, what's this? Hold on. All right, last thing. Right. I had this queued up just in case I had some extra time, which I don't really. But you guys know about Crash Course, right? Crash Course. Right. If you're really interested in engineering, you want to see a lot more in-depth detail on all this stuff. Again, my focus was mainly civil because that's more what I know about. There's this whole playlist on YouTube. So Crash Course, you can learn all about engineering. So I played a little bit of this earlier, but kind of out of time now. So there you go. Right. Engineering Crash Course. It's there. Enjoy.
Did this one have Hank or John Green in it?
No, here, I'll play like 20 seconds anyway. Here. But it's got
You
here.
live in a world of
Get an
creation.
engineer.
All of the things
So,
you see around me were created by people. The
I know, I
technology
like
we've
John
been
Green too, but
using
hey,
and what
he's an expert.
were
So.
likewise created.
Alright.
And not by lone
Yeah.
geniuses, but by whole teams sometimes entire generations of clever designers.
But, you know,
Those
Hank and
designers
John
were
Green,
engineers, and engineers are, when it comes
Yeah,
right down to
got
it,
it, yeah,
creative.
get it
The
done.
word engineering itself.
All right,
comes
well,
from
you guys enjoy.
engineering,
See you guys tomorrow.
cleverness, where engineering, meaning to